All right, we're going to break this lecture up into two parts, A and B. The first part here is going to be on design, and the second part stresses on an inclined plane. As far as the material for the semester goes, this is kind of a big deal as far as what you need to know for your first exam. Let's start off with talking about design, and I would expect you would have a design type problem on your first exam as well as a stress on an inclined plane type of problem. So we've been talking about stresses so far this semester and shearing stresses and axial normal stresses. We really haven't talked about how to use these in a design situation. So let's recast our stress problem. Sigma is equal to F over A in terms of a design problem. So that's just our basic formula for stress. If we know the force and the area of the cross-section, we can find the axial normal stress. But to turn this into a design problem, we can say suppose we want to find the diameter of a bar. If it's under axial loading so that it does not yield, if the force is 10,000 pounds and the yield stress is 50 ksi. All right, so we know how to work this. So we go over here and say, okay, I know my stress is 50 ksi, and that's equal to 10,000 pounds divided by the area of the cross-section, and in terms of the diameter, pi over 4 diameter squared, and we go and we work this, and we get a diameter of 0.505 inches. Okay, I went ahead and did that calculation ahead of time. Well, there's an assumption here that we've made that we may not have explicitly stated so far, and that's that the yield strength that's reported in material properties tables or by tests may be from a limited number of specimens, and it's often reported as an average value. In reality, if you were to test a bunch of specimens from the same batch of material, or different batches of materials even, you could have some variation in that yield strength. So to show this variation, it's probably easiest to draw what's called a normal distribution or normal probability curve. You may know this is a bell curve. Some objects work well, some materials work well with different kinds of distributions, but this is one that'll suit our purposes here. And so on the vertical axis is going to be the number of tests that we've conducted. And on this bottom axis would be the strength in KSI, the yield strength in particular for this example. And so what's often reported is the average value. And so this might be 50 KSI right here. So if we test a whole lot of these specimens, we might find that the average is around 50 KSI and the mode is around 50 KSI. We have the most specimens that fall at this value. But we have some that are a little bit stronger. And we have some over here that are a little bit not very strong, potentially even much less than 50 KSI. And there's a problem that we face when we have a design situation and we take these values as absolute numbers. And that's if we have a specimen that's weaker than 50 KSI, we're going to go ahead and yield that specimen when we put 10,000 pounds on it, or that axial bar that we have in our structure. So just to have here as a note, the problem is that sigma yield is usually reported as an average value. Okay. Well, there's a couple ways that we can deal with this. One method is if we have a documented statistical distribution for all of these different material properties that we may end up having, like the yield strength or the ultimate strength, and even different documentation of the variation in applied load, because that can vary too. We can account for the statistics involved in the material properties and the loads and the dimensions and everything else, and we can come up with a statistical based method to design our structure. And that's exactly what they do in a lot of companies. So, for example, an automotive company will take and they will instrument a vehicle and they will let a customer drive it, and they will measure the door slams, how hard the door gets slammed, how big of potholes the car goes over, what loads are induced in the suspension when the car goes over a pothole. And they will collect all that information and they will do statistics on it, and they will come up with usually a very severe representative customer, what they call sometimes the 99th percentile severity customer, and they will design their structure to that 99th percentile level, or it could be 99.9th percentile. That's usually an extrapolation from more regular users, but the idea is they can build in some extra safety, but while still recognizing that there's going to be some customers that may push their vehicle to very extremes, and they can't design for every situation, but they'll do the best that they can. So this is sometimes known as a load factor and resistance design approach to structural design, and it's a great method. Now, in our class, we don't have a background in statistics, so we're going to take a slightly different approach to this called the safety factor approach. There's a couple ways that we can denote this safety factor. It can either be on stress or it can be on load, but we're going to look at stress first. And the basic idea is that instead of designing our bar in the previous example to 50 KSI, we're going to design it to a smaller stress level than that failure stress, some allowable stress level. That will be that failure stress level. It could be ultimate strength or it could be yield strength, what have you. But we're going to take that and we're going to divide it by some number called the safety factor, where if the structure is safe, that safety factor is going to be greater than 1. All right, so again, that failure stress can be whatever you're defining failure to be. So in our example, we're going to do it on the yield stress, but we could do it on the ultimate, shearing stress as well, or what have you. So to continue that previous example, if we had a safety factor for that material in the previous problem of 2.0, then our allowable stress would be equal to 50 KSI divided by our safety factor of 2.0 would be 25 KSI. So now we're going to design our structure to 25 KSI as a limiting stress instead of 50. And if we do that in the previous example, then we'll get a diameter a little bit larger now, 0.714 inches. Now, there's some trade-offs with having too big of a safety factor. Obviously, the bigger we make our safety factor, the bigger the diameter is going to be. At some point, you're going to be beyond what you really ever would possibly need, and you'd be wasting material if you made a huge safety factor. So you want to keep it reasonable. Some kind of rules of thumb for safety factors. The more variability you might have in loads and in material properties, the bigger your safety factor might be. So for an example, a structure like a bridge, you may have a safety factor that might be 3 or 4 on particular components of that kind of bridge. It's a large piece of civil infrastructure. It lasts a long time, maybe 50 years or more before it gets replaced, and the loads may change on that over time. Truck loads may be increased, traffic levels may go up, so you don't really know exactly what's going to happen so many years in the future. If you know more information or have more stress analysis available, you can reduce that safety factor. So a component on a car might have a safety factor of 2, 1.5 to 2 maybe, depending on what component it is. Vehicles are very sensitive to fuel economy standards, so you don't want any extra material, but you may want to have some safety built in. Safety factor for a single-use component. An example that I like to give in class is when the space shuttle would fly. It used to have a single-use fuel tank. Safety factor on that, NASA had about 1.3 to 1.4. The smaller the safety factor, still greater than 1, the smaller what's called the margin of safety. So we can talk about that term as well. Okay, so in our case, if we had a safety factor of 2, we'd have a margin of safety of 1. If you have a really small safety factor, maybe 1.15, then you'd have a margin of safety of 0.15. Well, on stress, safety factors on stress is not the only way that we can have a safety factor. We can also have a safety factor on load, and it's defined in a similar way. We can say that the safety factor on load is our failure load divided by our safe allowable load. Now, for complex structures, you may get different results from a safety factor on stress and a safety factor on load. Very simple structures, they would amount to the same thing. So let's do an example here of a safety factor in typical type of mechanics and materials type of problem. But I think you'll see where the design knowledge comes in. All right, so here we are. It took a moment to get all this written down. But here's a very simple structure. It's a bar supported with a strut. The bar ABC is what we're going to call rigid. That means it just doesn't bend. And bar BD is a material that can stretch out. There's a load P on the end. Now there's two safety critical aspects to this structure. First one is bar BD. Bar BD has a rectangular cross-section of 2 inches by 1/4 of an inch, a yield strength of 36 KSI, and a safety factor of 3.0. So that means we want a minimum safety factor in that part of 3.0. The other safety critical feature of this structure is the pin over there at C. The pin over at C is in double shear. We've talked about what that means. The diameter of the pin that goes through it is 0.375 inches, has an ultimate shearing strength of 60 KSI, and a safety factor on shear, we want a minimum of 3.3. What we want to do is we want to find the biggest load, P, that we can apply to that structure so that both of those factors of safety are met in those respective components. At least those factors of safety. So what we're going to do, the general approach we're going to take, is we're going to treat this like it's two separate problems. First, we're going to take a look at bar BD and assume that that is the most critical component. We're going to find a force P that corresponds to bar BD going unsafe. Next, we're going to forget about that, and we're going to find a force P that causes pin at C to be unsafe. In the end, we're going to end up with two potential values for the load P. The answer that we want is going to be the minimum of those two possibilities. So one was on stress, on sigma for bar BD, and the other is going to be on shearing stress for pin C. If we pick the lower of those two possibilities, then we're going to be safe in both cases. So that's kind of the overall approach that we're going to take. Now we're going to get into the details. Well, like I said, first we're going to consider bar BD. All right, we need to find out a way to relate what goes on in bar BD to the applied load P on the left side of that structure. The way that we're going to do this is we're going to draw a free body diagram of ABC. So here's my horizontal bar, ABC. And when I draw a free body diagram, remember, a proper way to draw a free body diagram, what I want you to do is I want you to draw your own picture on your exam or in your homework, and you replace the supports with the appropriate reactions. So since we have a pin at C, we're going to have two perpendicular reactions, and it's going to be convenient to draw those vertically and horizontal. So we have, say, CX and CY. And when we remove the bar BD, since there's a pin at point B and there's a pin up here at point D, bar BD is a two-force member. A two-force member means that that reaction force that goes through BD, that internal force, acts along the physical direction of the bar. So the angle that this makes here, that angle theta, is going to be the same angle theta in this picture. We need to figure out what that angle is, so let's just do the tangent of theta is 40 over 30. Looks like we have a 3, 4, 5 triangle, and so we end up where we can calculate this angle theta to be 53.13 degrees. All right, so it looks at this moment like we have 4 unknowns. And we know from statics that we can have 3 equations for planar statics. But actually we know what the force BD has to be in order for bar BD to be safe. The force in bar BD is going to be the stress in bar BD times its cross-sectional area. Now the stress that we're going to have in bar BD is the allowable stress, which is going to be our 36 KSI divided by our safety factor of 3.0. The area of bar BD is 2 inches by 1/4 of an inch. So that's going to end up with a force in bar BD of 6,000 pounds. So now I know that this is 6,000 pounds. So now I have 3 equations and 3 unknowns. Now remember, I want to figure out what force P causes 6,000 pounds in bar BD. So probably the easiest way to do that is if I do the summation of moments about point C. You can do all the other equations too, but if we want to be a little bit efficient with our time, if we do it about point C, it'll have a zero-length moment arm and eliminate those reactions from our equilibrium equation. So I do the summation of moments about point C with that way positive. Since the distance to A to C is 60 inches, I'm going to have P times 60. I need to take a component of the force in the vertical direction. I'll have minus FBD sine theta times the distance of 30 inches to point B, equal to 0 for equilibrium. Now I know that FBD is 6,000 pounds, so if I put those numbers into my calculator and solve for P, well, let's go ahead and write the equation first. P is going to be 6,000 sine 53.13 degrees times 30 over 60. We're going to end up with 2,400 pounds. All right, so my P sigma right now is 2,400 pounds. I'm going to leave a little space here for the next part. All right, now the next thing that we should do is to go back and do the same thing for pin C. All right, so we want to find out how the shear force resultant at C relates to the applied force P. Again, we're going to draw a free body diagram. Let's just draw a new one. We have our reactions, Cy and Cx, and we have our force P that's applied to the structure, and we have the unknown force FBD off at that angle theta. Let's write down our equilibrium equations. Summation of forces in the x direction is going to give me FBD cosine theta plus Cx equal to 0. Summation of forces in the y direction minus P plus Cy plus FBD sine theta equal to 0. And we can do the summation of moments if we want, maybe about point C again. And then we'll have P times 60 minus FBD sine theta times 30 equal to 0. Now, if you notice, I did not put in the 6,000 pounds for FBD. You need to treat this like it's a separate problem. That's the critical load if the bar BD is the one that goes unsafe. But we don't know that it's going to be the same exact load where the pin goes unsafe. So we need to leave that in there, keep that in there as a variable. Now what I want is I want Cx and Cy in terms of P. In order to do that, let's first find FBD. If we find FBD, then we can find Cx and Cy. So FBD in terms of P will be equal to, let's see, I'll have P times 60 divided by 30 in the sine of theta, which was 53.13 degrees. If you put those numbers in the calculator, you get 2.5p. All right, now if I know that FBD is 2.5p, then I can solve for Cx. Cx is going to be equal to minus FBD cosine theta. I got minus 1.5p. And Cy is going to be equal to P minus FBD sine theta. And I got minus P for that. You should go ahead and check my algebra there. All right, so now I know Cx and Cy, but what I need to calculate the shear stress at the pin is the resultant of those forces. So the shear force at the pin is going to be the square root of the sum of the squares of Cx and Cy. Now in terms of P, if I put in minus 1.5 squared and I put in minus 1 squared, square each of those and take the square root, then I will end up with 1.083p. 1.803p. Now the shearing stress at the pin C is something that we can know the value of, at least the maximum safe shearing stress. That's going to be equal to our ultimate stress of 60 ksi divided by the safety factor of 3.3. Now we also know that we can calculate that based on the shear force. It's going to be the shear force at C divided by the area in shear. Now since this pin is in double shear, that's going to be 2 pi over 4 diameter squareds. So if we rearrange these numbers and put these all together, And knowing that V is equal to 1.803p, we will find a value for P based on the pin going unsafe of 2,230 pounds. All right, so that goes up in here now. So the answer to our problem then is, what's the biggest load that we can put on the structure so that both of those safety critical components remain safe? The answer is 2,230 pounds. Now there's lots of different ways that we can ask the same kind of design question. In this example, I gave you a couple safety critical components and you found the load that you could put on there. I could ask it the other way, where I give a load P on the end, and I could ask what are the safety factors that are in each of those safety critical components. So then you would calculate a safety factor on the bar BD and a safety factor on the pin C. So there's kind of a forwards way and a backwards way to ask these kind of things. But again, the basic idea with these design problems is we want to come up with a way to account for potential variability in loads to make sure that our structure is safe. All right, our next part of this lecture will be a separate video. Part B, we'll take a look at stresses on an inclined plane.